Now, knowing what energy is and knowing the different types of energy and the different equations for energy is very important for understanding energy. But more important than that is understanding how energy behaves, how it transforms. We can better understand the processes and changes that occur in nature if we analyze them in terms of energy changes, transformations from one form to another, or transfers from one location to another. Energy is kind of nature's way of keeping score. At the end of this video, you should have a good understanding of energy transfers and transformations. The amount of energy at the beginning of a process is the same as the amount of energy at the end. And you should be able to use energy conservation to calculate speeds and heights of objects. We're going to start by looking at energy transfers and transformations and then go into what is called the law of conservation of energy. So here we go. So imagine you've got a box and you're sliding this box across a floor. So when you push on a box and you slide it across the floor, you can feel yourself get tired. Clearly, you're using energy to move that box. In a general sense, we call the energy that you use chemical energy. Well, where does that energy go? You can feel yourself getting tired, so you can feel yourself getting lower on chemical energy, but where does that energy go? Well, it's easy to say, well, it goes into the box. But is that the whole story? Does all of the energy go into the box, or does some of it go somewhere else? To figure that out, we have to look at what type of energy the box has as it slides. Since it's moving, it has kinetic energy. But we also have to think that there's friction between the box and the floor. So as you slide that box across that floor, that friction can generate heat. So some of that chemical energy changes into heat energy. We call heat energy thermal energy. So some of that thermal energy from the box goes off into the environment. There's also a sound as the box slides across the floor. Okay? So some of that energy goes into making that sound. So from this we can see that when you push a box across the floor, some of the chemical energy that you use to push that box becomes different types of energy in that box, and some of that energy gets transferred off into the environment. We call this energy transfers and energy transformations. An energy transfer is when energy moves from one object to another, and an energy transformation is when energy changes from one type of energy to another type of energy. Think of lifting a pile driver. Work is done to raise the ram, giving it potential energy. That potential energy is then transformed into kinetic energy when it is let go and drops to the ground. That kinetic energy is then transformed into sound and heat when it hits, which are transferred into the ground and the environment. The same is true of a cannon being fired. When the chemical energy in the cannon is transferred to the cannon shell by work, that energy is transformed into kinetic energy, which then transforms into gravitational potential. So at the top of the path, there's less kinetic energy and more gravitational potential energy. Then back into more kinetic energy as the shell heads back to the ground. And finally, when the cannon shell hits, all that energy is transformed into heat energy and transferred into the environment. And really, we can see these energy transfers and transformations happening all around us. Chemical energy gets transformed into energy of motion. Kinetic energy, radiant energy from the sun gets transformed into chemical energy. We can have chemical energy again into motion with a car. We have electrical energy being transformed into thermal energy as we cook our food. And ultimately, all of the energy, all the different types of energy that we see in our universe, in our world, comes from, ultimately, the sun. That energy is transferred to the earth, where we can use it in all sorts of different types of potential energy and all kinds of different types of kinetic energy. Kinetic energy is just energy of motion, so even with like sound and light, those are just moving particles, so those particles all have kinetic energy. Now, if we could measure that amount of energy at the beginning of each of these examples and at the end, we would find that the two amounts of energy would be the same. That is, the same amount of energy exists at the start of each situation and at the end. We say that energy is conserved, and this is called the law of conservation of energy. We can easily see the law of conservation of energy if we look at an example where we eliminate as many conditions as we can that would cause energy to be transferred into the environment. For example, take the skater shown here. If we remove friction from this situation, no energy can be transformed into heat. So we call this kind of like an ideal situation. So when that skater is released from the highest point of this U-bend, his gravitational potential energy will be transformed into kinetic energy here at the bottom of the track, and then back into gravitational potential energy at the top of the track. And we can see that he rises to the exact same height on the other side. This tells us that no energy is being lost to other objects. His total amount of energy is the same at all points within that track. That's why he goes back up to the same height on the other side. This is because of the law of conservation of energy. And the law of conservation of energy states formally that energy cannot be created or destroyed. It may be transformed from one form to another, but the total amount never changes. So when we consider any system in its entirety, whether it be as simple as a swinging pendulum or as complex as an exploding supernova, its energy is not created or destroyed. It may change form, or it may simply be transferred from one place to another, but conventional wisdom tells us that the total energy score stays the same. The energy score takes into account the fact that the atoms that make up matter are themselves concentrated into little bundles of energy. When the nuclei, the cores of atoms, rearrange themselves, enormous amounts of energy can be released. The sun shines because of some of this nuclear energy is transformed into radiant energy. Enormous compression due to gravity and extremely high temperatures in the deep interior of the sun fuse the nuclei of hydrogen atoms together to form a helium nuclei. This is called thermonuclear fusion, a process that releases radiant energy, a small part of which reaches Earth. Part of the energy reaching Earth falls on plants and other photosynthetic organisms. And part of this is in turn later stored in the form of coal. Another part supports life in the food chain that begins with plants and other photosynthesizers. And part of this energy is later stored in oil. Part of this energy from the sun goes into the evaporation of water from the ocean. And part of this returns to Earth in rain that may be trapped behind a dam. By virtue of its elevated position, the water behind the dam has energy that may be used to power a generating plant below, where it's transformed to electrical energy. That energy travels through wires to homes, where it's used for lighting and heating and cooking and operating electrical gadgets. It's really amazing and wonderful that energy transforms from one form to another. And the whole process begins at our sun. What all this means then in the end for us is that in any situation, the amount of energy that we start with will equal the amount of energy we end with. For example, if I raise a boulder to the top of a cliff, I can figure out how fast it's going to be moving at the bottom if it falls off that cliff by taking the gravitational potential energy that it has at the top of the cliff and setting it equal to the kinetic energy that it has at the bottom of this cliff. We have to remember then our expression for gravitational potential energy is mgh, and kinetic energy is 1/2 mv squared. And we can see from this that we don't even need to know the mass of that boulder, because that mass is going to end up canceling in our calculation. Now, from here, we're going to take a look at different types of machines and something called efficiency in the next video. We'll see you in class.